that either.
You guys ready? Let's begin. Okay, this is my favorite part of class. So I love MCMC. So it is a very, very powerful tool for model builders. So people that write down complex posterior distributions. My complex distribution looks like pi theta. So you're imagining it's something complicated. Maybe it's high dimensional. So maybe theta over here is some high dimensional thing. My high dimensional representation is going to be theta 1, theta 2, theta 3. So mine is like 1848 high dimensional. Eventually, you know, we'll study problems with lots of covariance and stuff like that. So, but my 3 dimensions is supposed to represent something that's complex. Patrick?
I just want to check, did you mean to not post a video? Because you mentioned that you were going to.
Did it not come out?
I think you reposted Wednesday's lecture.
I reposted Wednesday's lecture.
Wednesday's lecture was up there twice.
Gotcha. Sorry about that, you guys. I meant to put up a real video, and so, like normal people, I just messed up. So, I probably had it sitting right next, dragged it in there. I probably wrote what the lecture was about. Oh, that changes everything. Okay, so I will repost that for you. But I'm going to recap anyway. So I was supposed to tell you what a Gibbs sampler was in Metropolis-Hastings. That's okay. So we're down a day, but we're going to catch up anyway. There's no need, we don't have to rush right now. We're in good shape on time. We're going to be able to get to everything I want to present. So no, I didn't mean to do that. Let's fix it up. So I'll tell you what I wrote down last time. The goal of MCMC, so I guess I should tell you what this stands for, since I didn't the first time. This is Markov chain Monte Carlo. Monte Carlo. So it's an algorithm, it's a stochastic algorithm. And it converges, and I shouldn't say it, I should say the whole collection of MCMC algorithms. And there's a whole bunch of different ones. And depending on the complexity of the distribution, you might select different algorithms. In fact, I'll tell you about one that's very general purpose. And there's these tunables that you can kind of build into your algorithm to get it to flex in just the right way, so that you sample from this distribution quickly. So like a lot of algorithms, this one is iterative, meaning it converges to sampling from this distribution. So why there's so many different algorithms is different spaces look more complicated than others. And so you want to come up with general purpose samplers that you can tweak and tune and make fit to your problem that you're sampling. So what a Bayesian usually does is they write down a likelihood function. That's easier said than done. In my class, we make that a triviality. And I tell you what f of x given theta is. And if you don't know that, you just have data, you have to piece together all these distributions that we talk about, maybe form a new distribution through mixtures, something like that, and then finally get something to resemble the data that you're looking at. So in reality, we have to build a model. Sometimes we have really good reasons in terms of mathematics that we want to study the average of something. So maybe we invoke the central limit theorem and we say everything's normally distributed and averages are normally distributed. Sometimes you might be building in physics into a system. So if you're studying maybe planetary motion, you might look at how planets actually move. But they warble around. The light we see is stochastic. It at least appears to be. It flickers at us. And so there's some error function. We might be able to describe that. So it kind of depends on the problem you're looking at. We kind of assume that we have a likelihood function. If I tell you what generated the data, you've got a likelihood function. And in my class, we can write it down. So in some classes, it might be so complicated that you can't write it down explicitly. And there's ways around that. There's MCMC for those type of processes. We won't be going into all these details. So the goal is sample from this. So once I have the likelihood, then I start thinking about which prior. So you might say, You know the nature of the parameters. If it's a location parameter, you might have some inclination of how to form a prior. Usually you pick something that's location invariant, something flat. If it's a scale parameter, then you do 1 over that scale parameter. If it had other characteristics that you knew about, you might have good reasons for formulating those priors. I'm going to tell you about other methods for coming up with priors that are fairly automated. And I think the automated ones people like to call objective, but there are choices that they're making. And there's properties that they're telling you your method will have. We'll go into all those details throughout. I think it's just a good time to break and show us something fun. So MCMC. So this is a Markov chain procedure. So if you know a lot about Markov chains, you're in good shape. If you don't, you're fine too. So let me just tell you what the Markov procedure is. So, or what the Markov property is. So Markov property say I have a collection of random variables. I'll say x1, x2, x3, so on and so forth, all the way down to some large number. I'll just call it xn. And I'm not saying that these things are IID. There's going to be some dependence between these variables. So the Markov property says that the random distribution, and I'll just call that P right here for probability density, or if you want a probability function, if it's continuous or discrete, it doesn't matter. So whatever this is, the probability of xj, I'll say, depending on everything else that happened before. So I'm kind of imagining that there's some xj right in here, there's something that happened previous, something that happens in the future, so on and so forth. This, depending on its past, x1, x2, all the way to xj minus 1. All the things leading up to xj only depend on the previous value. So this probability function, xj, given everything that happened before it, only depends on the previous time step. That's the Markovian problem. So I kind of like to think about physical examples. So kind of like if I'm walking around or something like that, it's like my step only depends on where I'm at right now. So I'm going to take this step right here. It only depends on where I previously was. Now I can take another step. And it doesn't matter what the sequence was. If I'm running, however, things are a little bit different. So if you're kind of running and you want to know where somebody's going to be, and let's say I catch my toe and I trip and I start stumbling, everything kind of depends on the way I'm stumbling and everything else. So now I'm thinking about a walk, and that might be Markovian. I can predict exactly where I'm going to land, just depending on where my foot is at some particular point in time. So these are nice. There's a lot of theory that we can develop for stochastic processes that only depend on the previous time step. And we can work out a lot of things analytically. We can do a lot of proofs. Things get a lot harder when things depend on everything. You can imagine. So it's nice to just be able to isolate everything and say the dependence only depends on one thing. Markov chain algorithms have that property. So they're Markov chains. Stochastic processes, they're not IID. They depend on their paths through just one point. Monte Carlo is kind of a fabricated word for describing this class of algorithms. So Monte Carlo algorithms are random algorithms. They're not the only randomized set of algorithms out there. There's other algorithms called Las Vegas algorithms. I may say something about them, but I'm not going to teach you too much about them. Markov, or Monte Carlo algorithms have a nice property that if I run them for a long time, they converge to our answers. Okay, so they're not just willy-nilly random, that it just does something crazy. Who knows what it does? It has a property that it converges to the right answer. All of our iterative algorithms are supposed to do that. The Monte Carlo property is such that the algorithm gives you a random answer in a fixed amount of time. And the longer I run it, the closer that random answer is to the truth, whatever I'm trying to converge to. We're all practical people. We never quite get there, but we get close enough to use something. That's true of all algorithms. So if you're only interested in knowing something to one decimal place, you would run the algorithm for less time than if you needed it to 1,000 decimal places. You'll never be able to compute something to 1,000 decimal places. You'll have a hard time computing things to 3 decimal places. So if you are, enumerating a lot of decimal places in your slideshows, get rid of that stuff, because you're probably not that precise. So you only want to report things up to, this is a reliable number. So Monte Carlo algorithms are random answers, are giving you random answers in a fixed amount of time. There's the Las Vegas class of algorithms, just to distinguish that, is it's going to give you, in a random amount of time, you'd like to say it gives you a fixed answer, it converges to the truth, but it actually really only gives you something within a certain tolerance with a probability attached to it. So you might be able to say, I'm within 4 decimal places, and I'm 99.999% sure of that. Okay. The rub with that is you have to wait a random amount of time for everything. So we don't like that. It's like, when's the algorithm going to finish running? Be anywhere between 2 seconds and 7 million years. And it can be like that. So we don't like that. So I'll teach you a little bit more about diagnostics to figure out if you've run everything long enough. We might come back to Las Vegas briefly. But because everything is running in a fixed amount of time, and maybe you can get some control on the air of everything, we like Monte Carlo algorithms. I'll just point out that this is a person, Markov, and Monte Carlo is a place. So those are always capitalized. You have a choice whether or not you want to capitalize the C. So if you put dots in here, you might make a different choice than if you end up just writing it down without dots. So this would be okay, and sometimes you'll see this. So if I put dots in there and I make it an initialism, then I usually capitalize. No big deal. But when you see that capitalized and that one not capitalized, somebody's making a mistake. You'll see the rookies do that kind of stuff. Which one gets capitalized? The one that's not a name. So Markov is an old probabilist, mathematician, and Monte Carlo is a place. So does anybody know where Monte Carlo is? Close. It's close. It is like the south of France.
Morocco.
It's not in Morocco. That one is in Africa. Monaco. Yeah. So where's Monaco? It's this little tiny sliver that lives right on the boundary of Italy and France. And there's a lot of casinos there. If you're into car racing, you certainly know where Monte Carlo is. They do an F1 race there. I had the great pleasure of getting to ride my bicycle on it, closed course, a long time ago. It was pretty cool. Lots of wealth was there. I tried to go into one of the casinos. I was wearing a pair of shorts. No way. So yachts filling everything. So lots of wealthy people are hanging out there. So Stan Olam, who kind of is one of the purveyors of Monte Carlo methods, was talking to his brother-in-law, needed a fancy glitzy word for random processes, and he told him about gambling, and he thought that was pretty cool. The Las Vegas variant of that is derived from the same rationale. So they're just describing random processes. That's the whole importance of it. Again, these algorithms are just designed to sample from some distribution. I've tried to convince you that if you can sample from a distribution, you can learn everything you want about it. So often if I want to learn about this distribution, if it's high dimensional in continuous, I have to do a lot of integrations. So expectations are integrals, variances are integrals. Finding intervals is areas under the curve. Those are integrals. And integrations are difficult to do in general. So So if I want to build up these general models, I don't want to be limited by my mathematics, my ability to write down the solutions. You might be thinking that you've learned numerical tricks in your math classes or in your computer science classes, your numerical analysis classes for approximating surfaces, and instead of integrating, you sum. Does anybody know any techniques like that?
Riemann Sums.
Riemann Sums. So that's the first one we learn. And so they use a basis function that's just a constant. They end up just summing over a histogram. Anybody know any other methods?
Trapezoidal rule.
What's that?
Trapezoidal rule.
Yeah, exactly. There's a whole bunch of them. So there's Gaussian basis functions. There's Simpson's rule that you would have learned. That uses a parabola, so it's got a little bit of curvature in there. The trouble with all of these methods is you're basically building a grid. And then you're filling in the grid with some sort of curved surface or something flat. And if you made your grid infinitely precise, you would get the original function value. And that's not too hard to do in one dimension, but as you move to 2 dimensions, everything gets a lot harder. There's a lot bigger pockets of space. How much? It's squared. So the amount of effort, let's say I needed to do 10 iterations, which you'd never have. That's never enough in any of these methods. If I had to do 10 iterations to get some precision of answer in a one-dimensional space, I'd need to do 100 iterations in a planar space, in a two-dimensional space. In cubic space, things are a lot harder. So you end up having to refine the grid more and more and more. Monte Carlo methods are competitive with quadrature techniques, these grid-based methods, up to about 3 dimensions. And after that, Monte Carlo wins. So just so you know, in your math class, all those techniques, they work out pretty good at about 3 or less dimensions. You move to 7 dimensions, it doesn't work very well. So this does not suffer a curse of dimensionality. We won't prove that here. But it doesn't suffer the same curse of dimensionality as quadrature techniques. So it's just a different brand. What I like about these techniques is they're usually easier to implement than quadrature techniques. So I don't have to work in tensor spaces, so on and so forth. I want to just point out that this class of algorithms that we're going to be studying are extremely important. And it's not just according to me because I built my career off of them, but somebody else said this as well. So back in the year 2000, turn of the century, now it seems like an awfully long time ago, Stanford had put out a course called the Top 10 Algorithms. And I took that course because I thought it was pretty cool. And I learned about 10 different algorithms, and I learned them kind of okay, you know. And so it takes a while to understand all the nuances in all these algorithms. But I remember learning that this was the most important algorithm of the 20th century. I'm not sure if that's true. There's certainly a lot of algorithms out there. Different universities have been teaching this course, and there's a lot of literature going through all of these different algorithms in the ranking. The IEEE came up with this, so they had some board of engineers, computational wizards, and they decided to rank them in the way that they're ranked. So all we really know is that it's really important. And so you can just do a search on the top 10 algorithms. You're always going to come up with this list. This is it. So maybe in 100 years we'll have different algorithms, but these are really important algorithms. And some of you may have seen some of these. Metropolis is right at the top. Any which way you cut it, it's an important class of algorithms. I imagine one of these days somebody's going to win a Nobel Prize that has worked on some of these algorithms. And in fact, Parisi ended up winning a Nobel Prize in physics for climate change modeling. And he's one of the inventors of what's called simulated annealing, which is a close cousin to MCMC algorithms. We might talk about those. So we're getting closer to somebody getting a big award for working on these algorithms, but it's changed everything. So Bayesians used to argue about the likelihood principle or regularizing through priors and all these philosophical reasons you want to be a Bayesian, and we kind of kicked off there. But I would say the biggest reason you want to be a Bayesian nowadays is all that good stuff, but you can actually compute your answers. And so you can actually do it. So that's probably the thing that switched a lot of minds. Probably wasn't the decision theory aspects. It was just the practicalities. Now you can do this. So this is the savior for Bayesians. We can learn about our posteriors, even though they might be represented as some big hierarchical model. So I write it down as pi here, but there might be a lot of lines of math showing dependencies between the parameters. And doing those integrals might be something that is just impossible. And so these algorithms will help you. So you can build crazy likelihood functions and work with really cumbersome priors, possibly stick everything into these algorithms. You can still sample from your distribution, compute whatever you want to compute. Intervals, variances, means, or the 17th moment of some distribution if you wanted that. So basically, if you can understand the shape of that curve, you can compute anything you want. Okay, I'll just point out, here's another place right here. So SciAm News, the applied mathematicians in here read SciAm. It's a big deal journal to numericists. So best of the 20th century, editors name the top 10 algorithms. And same thing, Metropolis algorithm. When I say Metropolis, I mean Metropolis-Hastings. It's the more general variant. That's what we're going to study right now. So let me tell you what these algorithms are, and then I'll start filling in the details. Let me just show you real quick before I tell you any details, just so you can get a picture in your head of what's going on. So let's just think about an example. We've been studying this example for a while. Okay, so here's an example. This is relatively easy, but I think it'll demonstrate the case. Xi's come from a normal distribution with two parameters. If you don't like this, that's okay. 1 over phi is usually how I parameterize the variance term, so I flip it upside down. I've got a lot of observations from this. If you think this is too simple of a model, you can make it multivariate, so that you have a vector right here, and instead of a scalar right there, you'd have a matrix, and you need to fill in all those values. And so you can turn this example into something high-dimensional real quickly. A lot of literature surrounds this. We'll be looking at a higher dimensional analog of this in the coming days. That's what that Gelfand and Smith paper is about, and I'll introduce you to that. So, the goal might be to understand whatever this means. Pi, mu, phi, given x. So I might want to write down what this thing is. What does it look like? It looks something like this. So I'll just write down product. I goes from 1 to n, p 1/2, e to the minus 1/2, xi's minus mu, squared. Put my phi upstairs right here, my precision. That's my likelihood. And then I got my priors, whatever they are. So maybe 1 times 1 over phi. That's what I would typically use in this example. So I always say there's lots of generalities and you might choose to do something, but if nobody told me anything about what mu and phi could have been, I would just default on these reference choices. So they're Jeffrey's priors, their scale and location and variance, so lots of good things going on there. We'll talk about the other technicalities in a week or so. So this model right here, so I'll just write this down. Again, this is phi to the n over 2 minus 1, e to the minus phi. I'll write it down maybe like this, and we'll just leave it the same. Over 2, sum, I goes from 1 to n, xi's minus mu squared. There's my prior right there. And so I might want to understand what this function looks like. And in a previous homework, I asked you to sample from this distribution. And then I forgot, I didn't tell you how. So this is the answer to it. MCMC algorithms can be tuned to converge very fast in some cases. In my example that I'm going to show to you, and I'll walk you through these details next time, I purposefully made my algorithm a little bit slow so that you can see certain aspects. And in fact, I've combined the Metropolis-Hastings algorithm with Gibbs. So they're all part of the same class, and you can combine them together. I'll tell you why you want to do that, at least by the end of today. So let me just show you a quick example. So this is what you would get. So without any understanding any of what's under the hood, I'll walk you through this later. There's a few lines of code. I've got a lot of lines in here just so that you can read through it. There's plotting functions. Most of the code is plotting stuff and storing the data. So there's really just 2 lines of code that are really doing anything that's fancy. I'll walk you through those later. And I illustrate some points. I have things done on log scales so that it doesn't numerically explode. And I have some little toggles in here so that I can do it in a non-numerically stable way. So there are implementation details that we'll walk through. This is what the algorithm will do. So I'm going to take some data right here. So the idea is I'm going to plug in data. That's going to be called X. I know what the truth is because I'm going to simulate this data. So I know what mu and what sigma are. I simulate it, and the only places in my code that I use the truth are in plotting, so that you can see where the truth is, and then you can see where the algorithm converges to. So let's just generate some data first. So X is going to be random. I'll get maybe 20 data points. So this does 20 IID from a normal, 0, 1. I'm going to multiply by sigma, so it's going to give me variance sigma squared. And I'm going to shift everything by mu. You can input those into rand n, but I always just start with those. It does the exact same thing. So you can see where all this stuff is. I should probably generate a true sigma. Usually we don't get to know this. I'll say 2. And true mu, we can change these numbers a little bit later. True mu, let's make that 7. So I'll generate some new data. Boom, I've got 20 data points. They look like this. So, pretty small example. So this should work pretty well. If I wanted to look at the mean of everything, mean of X is 6.3, so it's not exactly 7. I only have 10 data points. So there's a little bit of jitter in there. If I wanted to look at the variance of X is about 4, which is 2 squared. So they're not exact. If I get more and more data, those things start to converge to the truth. And so Bayesian wants to give you more than this. They want to give you the full posterior distribution and show you the dependence between these parameters. So I don't know an automatic way to sample from both of these things. They give me good samples every single draw, so you might build up an MCMC sampler for this sort of example. This is probably overkill. I've also set up my sampler so it runs a little bit slow so you can see it evolve. I need to initialize my algorithm, so we have to say where it starts from, and then my samples will start to converge. We'll play around a little bit with that, but I have at the top of my code some initializations. So I've got mu in it and phi in it. So I've actually cheated right here and I've plugged in the truth. And so I'll show you what it looks like when I don't plug in the truth. Obviously, if you start at the truth, this algorithm is going to converge really fast. You never get to do that. So we want to set up our algorithm so that we start somewhere very far from the truth and converge. So let's just run it. We've got the oracle on our side telling us a good starting point. So again, this is optimistic, but I'll just run everything. Here's my truth right here. It's the center of the screen. It's that red dot. So phi right here is 1/4. So sigma is 2. The variance is 4. 1/4 is 0.25. That's this. And mu is 7. That's where that lines up. Hopefully you can see that. I'm going to take a step, and I'm just going to run my algorithm. And I'll show you what this is doing through a sequence of lectures. It'll probably take me at least another time to get through everything, but I will post that video for you. So basically, it's sampling from this posterior distribution right here. And this is actually what this looks like right here. If I were to draw samples from this distribution, it looks like this. It's got this triangular shape, which is kind of cool. So I've shown you two things. I plotted my samples, but in this other frame, I was plotting the trajectory of the samples. I'll walk you through these plots in a second. But these are just the trajectory of my samples, and I'm always plotting for you the last 1,000 so you can watch where everything is. So let me just say a few things about this distribution. It's not a circle or something like that in our ellipse. These samples are not independent of each other, phi and mu. There's dependence. And it kind of makes sense. So if I think that the precision is low, what I'm thinking is the variance is high. And so the variance is high in the x's if I think the precision is low. And so my uncertainty about mu gets bigger right here. If I go in the other direction and phi were large, up towards the top of everything, that means that the variance is small. So that's what I believe, the variance is small. And then I have more precision in mu. I'm more precise about it, so those intervals are tighter. And so this distribution describes that. And I kind of like that. So we can see the joint relationship between mu and phi. These are the marginal distributions right here. So instead of plotting everything in a bivariate manner, I plotted everything in a univariate manner. These are called trace plots right here. And what we want to see is fuzzy caterpillars. I'm going to show you some bad examples in a little bit. But this is converging very, very nicely. And so it's fuzzy caterpillar, that means everything is stationary. I'm sampling and it's staying in about the same region, it's not drifting. So probably should show you bad examples before good examples, but this is working pretty well. I plotted for you the truth. So here's 7. This plot is for mu, right here. Why isn't this right in the middle of the distribution? So there's the truth, and here's my marginal distribution. So I've taken I'm getting bivariate outcomes, and I'm just plotting everything for mu. So that marginalizes everything automatically, as we've kind of discussed. So that's the nice thing. If I have joint samplers, I have marginal samplers, just by focusing on that column. Does anybody know what distribution this is following right here for mu? It's not normal. So it's the marginal distribution for mu given the data. So that means I'm integrating out phi. So we've done that before. We've seen that distribution, but if I didn't know how to do that math,
Student T?
it's T. Yeah, this is a T distribution. If I didn't know that, that would be okay. This is distributed as a T. It's not normal because it's the integration over phi, or sigma squared, however you like to think about it. This right here is a gamma distribution, and that's what you worked off on the previous homework. So it's like n minus 1 over 2 s squared over n minus 1 is supposed to be the gamma that you get. So if you missed a -1 sign, the TA would point it out to you. So several of you did. I've looked through a few of them, but we'll get that all cleared up soon. Yeah, you're very close. So I did look at yours. So yeah, it's easy to drop a -1 in there. If you didn't know how to do all those integrals, this stuff is supposed to work out right for you. My code does work in this example. Let me just show you while we're at it what it looks like if I start from somewhere else, so you can kind of get the idea of what a Markov chain is doing. We'll talk about burn-in and all of that, iterations, step sizes, all of that. There's all kinds of tunables in my variant of this algorithm. Let's start somewhere else. So I'll say true mu plus 10. Okay? So I'm going to start some number of steps away from the truth. I'll start right there. I'll just add 10 to everything. So mess everything up a little bit. Let's run again. So So this algorithm started way over here. It shot down that trajectory, and bang, it found that red point. And it's building that same distribution. So if I zoomed in on this, you'd see that same triangular distribution. Here's my samples, right here. Boom, boom, boom. And then eventually it converges to something. And once everything got there, it stayed there. You can kind of see that in this picture right here that I was drawing for you. It went down, it got there, and it never jumped away. So MCMC is not converging to a point, it's converging to a distribution. Patrick.
So why is mu not converging to truth?
It's converging to the true posterior. So back to my earlier question, Patrick's thinking about why wasn't the 7 right in the middle of the distribution? So I run it for a very, very long time. Patrick thinks maybe it should converge in on 7 and just get tight right around there. Why is it not doing that?
The sample is, it's got some randomness to it.
I have 20 data points. So if n went to infinity, I would converge in on 7 real closely. But I'm uncertain about 7. And so what I'm actually getting is a description of my uncertainty. And so it'd be very strange for the true answer with a small sample size to live right in the middle. But if I had a huge sample size, this thing would, the uncertainty in my distribution would be a lot more compressed. Does that make sense?
Yeah.
So it's basically the stochasticity in the sample. So it doesn't converge to a number, it converges to a distribution. So when I run this right here, I've got all this junk. You can see those samples right there in the very beginning. I can see these samples right here. It converges relatively quick. But all this stuff right here that I saw early in the distribution, that's all trash and I need to throw it away. That's called the burn-in period. So, and that's stuff you throw away. So Markov chains limit to some distribution. If you know about Markov chain theory, what we're actually stepping through is a limiting distribution that under very preliminary assumptions is called the stationary distribution. We'll walk through these assumptions, but they're statements of ergodicity. And I'll tell you what all that is soon. If you develop your algorithm right, those distributions are the same, the limiting distribution exists, and it converges to the stationary distribution. If you don't know about Markov chains, that's a lot to hear all at once. But ultimately, you're getting that this thing converges to some distribution. Let's just start this thing farther away. And if I had messed up my code and I had a lot of numerical problems, this would be a huge issue for me to start very far away. I think this code is robust enough that it'll actually work. So let me just run one more time. Boom. Started very far away. Here's my red dot right over here. It still made it. So it's converging to that. I have more burn-in stuff that I need to do. So I need to run it for longer because I've started farther away. When you code this up the way that I instruct you to in the homework, your stuff is going to converge in like 2 or 3 steps. Okay, so I just want you to see that it depends on your initial value, but I've set my code up to converge slowly. And I'll tell you how I did that later. So here's my, just real quick. This is my stuff I need to chop off right here. So I need to get rid of that. So plotting the histogram with this whole thing in here, it shows this big tail, you can barely see it. I want to throw that stuff away. This histogram is not converged to the truth because I have all this junk. Easy solution, throw it away. Please.
Why doesn't it just go straight to the distribution? Why does it go straight down?
Yeah, that's interesting. It's telling me about what the tail looks like in this. So it turns out the tail is a little bit steeper in this direction. So it's walking up this tail and then it hooks over here. So it's telling you a little bit about the topology of that and the steepness of everything. So it's not just doing a gradient walk, but it has something to do with that. That it ends up, this is the massy part of the tail it follows. It follows. So basically it's telling you about the convergence rate of both parameters. So what's kind of interesting is it converges in phi space faster than it converges in mu space. So it didn't block the diagonal. So it's converging in the variance first, and then mu. And all problems will be like this. In MCMC, everything has to converge before you can do any inference. So all of your parameters have to converge, and they'll converge at different rates. So if you're an MCMC person, that's what you'll study, is rates of convergence, or at least proxies for, when you're trying to speed that up. So what we normally do is we chop everything off. I've got this little toggle in here that says burn-in. 10,000, I'm just going to say the burn-in was 10,000 steps, see how it all looks, and I'm going to throw everything away before the 10,000 steps. So that little toggle right there just truncates the vectors it returns. So let's just have a look and see how this works. It's converging, boom. We'll see if that was enough, but usually this is an iterative process itself, just running these algorithms. Usually you just crank these numbers up, let it run for a long time. So still have a lot of stuff right here. I still need to throw away more samples. So burn-in wasn't long enough. I still have this big tail right here. So I need to throw these things away too. So I'm going to crank this number up, maybe 20,000 samples of burn-in, throw those things away, rerun it. This is the life of somebody that programs MCMCs. Is rerun, look at it, rerun, look at it, rerun, look at it. The longer it takes your code to run, the longer you have to wait to figure out that you've got a problem. So almost there. I need to chop off a little bit more. One more time, just to get the point. So usually you have to do this. So I'll make that 30,000. Rerun it again. What you would normally do is probably start closer to the truth. But what I'm trying to exemplify is your code should operate and be able to start very far from the truth and still converge. Boom. I ripped off enough, so I still plotted it a little bit for you. Probably should tear off a little bit more, but this looks pretty good right here. I did plot everything for you so you can see it, but these histograms I'd be willing to report at this point. So that's the idea of MCMC. My algorithm that I've coded up here is a hybrid Gibbs Metropolis sampler. Let me take the last couple minutes and just tell you what these algorithms do. So both of them need initializations. We need to start somewhere. So, and I'll tell you about that in a second. But here's what a Gibbs sampler does. Is it ends up sampling first theta 1, and it samples from its full conditional distribution. Theta 1, given all of my data, it's going to be conditioned on theta 2 and theta 3. The question is which theta 2 and theta 3 you plug in here. You actually plug in your initial values. So these are to be initialized on the first step. So on the first step, I need to initialize theta 2, 0, and theta 3, 0. So in general, in a Gibbs sampler, if you have 3 things that you're updating, you need to initialize 2 of them. Let me say that again. In general, if you have k things that you're updating, you need to initialize k minus 1 things. So the other steps are very similar. Theta 2 is going to get updated. So this is a sequential sampler that updates the random variables in some order. This is going to be theta 1 I'm going to condition on, and theta 3. Which theta 1 do I plug in? You're actually going to take this most recent value you have and plug it in right here. So I'm going to take theta 1t. Theta 3 hasn't been updated yet, so I'm just going to take my previous value. Theta 3, we're going to update from its full conditional. theta 1 and theta 2, which theta 1 and theta 2, I'm going to take my most recent values. So I'm going to take this theta 2 and I'm going to plug it in right here. Gibbs has done something very important for us. It's taken a high dimensional distribution and it's broken it up into small dimensional distributions. So in this case, 3-dimensional problem that we're studying, and all I have to do is sample from 3 scalar distributions, 3 1D distributions. Generally, that's easier to do than sampling from something that's joint. And so, again, these are all the full conditionals. The assumption here is that I know how to sample from those. So, for our example, what this looks like, it's the same example. So our normal example, normal mu phi. We want to get these xi's from this. What we're going to do is we're going to sample mu t. It's going to come from its full conditional distribution. Mu given x and phi. Which phi? My most current value. So I'll have to initialize that and pick it to be somewhere, just like we did in my code. So I was initializing 2 things in my code, but only one of those values was being used. And it depends on which one I update first. You're going to ask, does it matter which ones you update first? It can. So the rates of convergence have something to do with something. So in general, you don't know what they are. So we consider this usually just experiment with it and see which ones you should update first. It shouldn't matter in any real important way. Theoretically, does it make a difference? It does.
So for mu, are we taking the map then? The value we're placing in mu, or what?
What do you mean?
Because you're saying we're sampling mu from the distribution, right?
Right.
So are we randomly sampling, or are we taking the maximum?
No, we're sampling from it. So what is this distribution here? I'll write down the other one just so that we have some more work to do. What is this distribution? In my example with my priors, I could work this out. This is a normal x bar, and this is going to have parameter phi, t minus 1 in there, divided by n. So this is the variance over n. So I'm taking its full conditional, so I have to do a little bit of math up front, but the beauty of full conditionals is I don't have to do any integrals. So we did this in the first week of class. So I'm not grabbing a map or anything, I'm just sampling from this normal. How do I sample from that normal? I push the button on my computer. Usually people use the Box-Mueller algorithm if you know anything about it. So what the Box-Mueller algorithm does is for 2 uniforms, it'll give you 2 normals. So for the price of 2 uniforms, it can convert them into 2 normals. There's a polar coordinate transform that does that. So hopefully you know how to sample from normals. If you don't, R knows how to do it. MATLAB knows how to do it. Every standard package out there knows how to do it. So this one right here comes from its full conditional. And I'm going to plug in my most recent value of mu right here. So I'm going to take this thing and plug it in. And this thing is going to come back around and sweep through that. What's this distribution? We worked that one out. I can do it in my head. It's a gamma. And the question is which gamma? You'd have to work through it. It's n over 2. And then this has the sum of squares. I'll make that a little bit bigger so you can see it. This other thing right here is the sum of the xi's minus mu t squared over n. So it's this sum of squared business. No, over 2. And that's what it is. That's what we worked out. So working these out isn't difficult in this problem. You probably know how to sample from a gamma. I'm out of time, Let me tell you what Metropolis does for us. If we don't know how to sample from any of these distributions, Metropolis is a procedure for being able to propose something, some distribution that maybe kind of looks like your distribution that you're trying to sample from. It doesn't have to be that good of an approximation, but just something that lives in the same space. And what it does is it corrects up those samples for you so that you can sample from these things right here. So it's a general purpose sampler for when you don't know how to directly sample from a distribution. And so, and there's some set of rules. I'll put the video up if you want to just give 20 minutes into the video, and it'll tell you what that rule is. And so, next time I'll start up here, tell you about Metropolis. In my code, what it's doing is it's doing these two updates. And even though I know how to sample from these distributions, what I've done is I've built in a Metropolis layer on both of them, and I've made my Metropolis converge very slowly. So, and I'll tell you all about it. So I did that just so you can see it converge. I could make it really fast if I ended up plugging these things in, which you'll do on your homework. It'll converge almost instantly. I think it converges in 2 or 3 samples. My sampler takes a long time to converge because I ended up using Metropolis steps that I didn't need to. So we'll come back next time and discuss all of that. One last point I want to just point out to you. Gibbs is Metropolis in disguise. And so, but I have to tell you all these details next time. That's it for now, you guys. Sorry about the clumsy mistake. I'll have that up in a couple hours.